Hello. We're on the fifth lecture, but it's lecture number 4 in the topics. Welcome. So last week we did copying, we did some extensions and mostly Baker incremental copying and replication copying, and we started to do generations. Today we'll finish that and also extend to the train algorithm and hopefully be able to start with concurrency. So this is the plan. So like I said last week, most programs behave in a manner where most objects die young, and therefore a logical way to work with it is to just separate the objects by age and collect the young objects more frequently. So this is what we're going to do. So the heap will be divided into 2 or more areas, which we call generations. And the objects are allocated in the youngest generation. These are the youngest objects. And this youngest generation, the young generation, is collected very frequently. And we expect to be very efficient because we expect lots of them to be garbage already, unreachable. Objects that survive in a generation long enough, which is like heuristics, are promoted to an older generation. But usually we just use 2 generations. We have the young and the old, and objects are promoted to the old generation, and that's enough. And the advantages are that mostly we have short pauses because we collect the young generation, which is smaller. And also in terms of efficiency, we concentrate our efforts where we expect a lot of objects to be unreachable that we can reclaim. And from locality point of view, the collector is working on a small part of the heap, which improves locality. And also the program works on the same area because the program allocates space here and it usually modifies young objects, new objects, rather than go to old objects and make changes in them. This is what just happens normally. It's not a mathematical thing. It's just how programs behave. And this is really very, very useful. Almost all garbage collectors that you'll see in production nowadays will have generational collections. So how do we do this? So we went through a simple example. Let me do it again. So suppose we have the young generation as a semi-space here, from space and to space, and this is the old generation. And we note that there is like a pointer between generations, from the old generation to the young generation, that we have to consider because it may imply that this object is alive. And so when we do the first young generation collection, all of these 4 objects are expected to go down to the second semi-space, and this guy too, and this guy is not reachable and should disappear. So this is what happens. So A, B, C, and D are copied. And now the program takes responsibility for the execution, and the program starts by erasing this pointer, which makes B unreachable. And then the program allocates X, which we'll put here, and it will then create a pointer between A and X. So this is, and now we do a next collection, a second collection. And then what we expect is that these 2, so A, C, and X are alive, and also D are alive. B should disappear. But the promotion strategy here is if someone is managed to survive for 2 collections in the young generation, it is promoted. So we have A, C, and D surviving for 2 collections. They should go up to the old generation, and X should go to the new the young generation. So this is how it goes. X goes here, A, C, and D go to the old generation. This is a simple, very simple example, and I hope it makes things clear. Okay, so we have two issues. One of, yeah, what about? Age? What do you mean age? Age. We did not do a collection of the old generation, and so it remains there forever until we do a collection of the old generations. There will be lots of collections of the young generation, and dead objects in the old generations will remain there until we do a collection. Yeah, it's a good question. Okay, so there are two issues that we have to solve. One of them is that we need to consider intergenerational pointers, pointers that go from the old generation to the young generation, and maybe vice versa. We'll talk about this. And we have to talk about promotion policies. When do we promote an object? So these are two things. So the intergenerational pointer is the main difficulty. So there are pointers from old to young objects may imply liveness of the young objects, and we collect only the young generation. Now, we don't want to go over the old generation to decide if objects there are dead or alive. If there is any pointer from old to young, we conservatively decide that the young object is alive. So we don't want to trace the old generation. So the idea is that we'll keep a record of all pointers from old generation to young generation, and we'll use that to decide which objects are reachable in the young generation. This is going to become as like it's additional roots. These are things that we decide that are reachable, and we don't question that, and we just trace from them everything that's reachable from them for us is alive. Okay, so this is the, and there is another property of programs that most pointers are from young to old, because we allocate things in the young generation and we start changing pointers, installing pointers in the new objects. Most of the pointers are from young to old. We seldom go to the old generation and start installing pointers to the young generation. And so this is good for us because we are recording, we're going to record pointers from old to young, and there will not be a lot of those. This is going to be good. So we only keep record of pointers from the old to the young. We do not keep records of from the young to the old, and therefore we cannot reclaim the old generation without doing the young, because we just don't know what points from the young to the old. Okay, so we collect the young generation together with the old generation just because we do not want to maintain a list of all the pointers from the young generation to the old generation and reclaim the old generation separately. So we just collect them together. And the good thing is that we don't need to record all these pointers from young to old, which there's a lot more than old to young, usually for programs. And there is a small cost because the young area is small and the old generation is large. So if we just add this small young generation to the collection, we don't lose a lot in efficiency. Okay, so this is how we handle it. When are they created? Intergenerational pointers are created during, they could be created by the program or by the collector. By the program, it's when you write a pointer. It may be a pointer, the program writes a pointer. It may be a pointer that resides in the old generation and points to the young generation. That means an intergenerational pointer has been created, and that has to be reported to the collector. So we record each such thing by using a write barrier. Whenever there is a writing of a pointer, I think there is an example here. If we write an object into some field, we check if the field, the pointer field, is in the old space and the object is in the young space, and then we record it for the collector. We created an intergenerational pointer, and the collector has to know about it. So this is a possibility. It's just an example. So we have a right barrier for all of those. It can also happen that the collector promotes an object to the old generation, and that object has a pointer to the young generation. So the collector can also create intergenerational pointer, and then it has to record this pointer for itself. So both of them are doing that, and we just have a record of intergenerational pointers. Okay? Makes sense. So we have all of them listed. How do we, so the saving in costs is first that we don't monitor pointer modifications on the stack, on local roots. We don't need to do that because whenever we do a young or full generation, a young generational collection or full heap collection, we scan the roots. So we don't need to know to record, to keep a record of all pointers from the roots to the heap. We just scan them all the time. And this is very important that we do not have a right barrier on our local variables because they change a lot. If we put a right barrier on the local variables, on the roots, then this is a big overhead that we do not want to do. And all over the course, we'll try to avoid monitoring pointer modifications on the local variables in the roots. So here we don't need it. And we also do not record pointers from the young generation to the old generation because we collect the old together with the young, and so we don't need to know if the young points to old. And this buys us another saving because most of the pointers are from young to old, the intergenerational pointers. And so these are the two savings that we get by doing it right. Okay? Which one? The one. So, and this is stressed here, we don't want to use a right barrier on local variables, right? So if we look at the picture, there is like the heap, there is like old, and there's young, and there is roots here, which is usually a lot smaller than the heap, a lot smaller. So it can, point the stack and the local the local variables are usually on the stacks. The roots, we said we do not want to really say in each programming language it's different. Sometimes it's global variables, sometimes it's all kinds of things of the programming languages. For us, it's something abstract that the programming language gives us, and so but usually it has at least the registers and the stack. So this points to various objects, and all the reachability is determined by that. But these change a lot. And so we are going to monitor all pointers that are intergenerational between the old and the young. So we're going to have a right barrier that will make sure we have a list of all such pointers, but we don't want to monitor all changes to the roots. If we monitor that, it will take a lot of time. If we do a right barrier on each modification of a local variable, then it's going to give us a huge overhead and the program is going to run slowly. And this thing that we avoid the right barrier on the local variables is something that we're going to try and do in all our garbage collectors. And sometimes it will be more problematic. Here, it's really easy because we just don't need it. Because whenever we collect the young generation, we're just going to scan the roots. The roots are much smaller than the heap and even the young generation. And so we just scan them whenever we want to do a young generation or a full generation or a full heap collection. Okay. So this is so how do we record the pointers? There are 4 standard ways to do it, and let's go over them. So the first one is remembered sets. This is just I remember the locations of pointers that go from old to young. I just remember the locations, and usually I do not want to have. So there's a right barrier, and I find that something is going to point from old to young. I do not want to keep one location many times in the records if it's changing all the time. I want to keep it only once. So I could keep a bit in the object header to tell me if it's already in the records, and then I will not put it there again. This is to avoid duplicates. And I want to remove irrelevant entries during the collection. And this is something that soon you will tell me how. Let's look at how it looks. So if I have a remembered set, it could point to an object that has intergenerational pointers, or it could point to actual locations. That is fine. Both of them are fine. It depends on engineering issues. But you could think also of pointing to say this is a target of an intergenerational pointer. I could record that one just to know that it's alive. But this doesn't work. Someone has, you can't work with it. Someone has an idea why this doesn't work well if I just keep these? Okay. Right. One thing that could be problematic is that if it's like a copying collector, this moves between collections, but you could think that we could, keep updating this to point to the same object, even though we move it. But it's something we cannot do. So, yeah. Right, that's exactly the problem. Okay, so what can happen is, suppose we have this pointer to the young generation, and it changes, now it points to this guy. So if I keep the location of this, I can tell that, this pointer has changed. This is not anymore, okay, this is pointed from two locations, so it's not so good, but both of them could change. And then this guy will not anymore be a target of an intergenerational pointer, but I will never know it. If I just have a pointer to this, I cannot tell that it's not anymore a target of an intergenerational pointer. But if I keep these, and during garbage collection, I only go through these, I can see what the intergenerational pointers are. So for example, if this is changed to point to here and it's not an intergenerational pointer anymore, I can remove it from the remembered set when I do the collection. So it is important to keep either the object or the exact field that is pointing to the young generation, but I cannot just keep the object in the young generation because I will never know if it's not anymore a target of an intergenerational pointer. So this is what it says in the previous slide. We remove irrelevant entries during the collection. We just go to trace them and we see that they don't point to the young generation anymore, and we can remove them from the remembered set. So this is how it works. The properties, it's good for the collector because the collector can just go through the set and it has all the intergenerational pointers. And so you don't know the other options, so it's not clear yet why it's good for the collector, but soon you will see that this is good for the collector, and it's bad for the program because a write barrier that adds to a set is usually, I don't know, you can think of a skip list or a hash or something. It takes time to work with it, and soon we'll see better options for the program. Yeah. The program is just changing a pointer from the point of view of the programmer, but under the hoods there is a write barrier that is added to this pointer modification, and the write barrier has to add this intergenerational pointer to the set. That takes time that the program has to go through. Okay. So let's go to the second method. The second method is called card marking. So we divide the heap into cards, just logically, and suppose each of them is 1 kilobyte in size, and we have a card table with 1 bit per card. And now, whenever the collector, whenever the program whenever the program, so the meaning of this bit per card says can there be an intergenerational pointer in this card? So whenever the program changes a pointer that makes it an intergenerational pointer, or you can just say maybe for all changes of pointers, I just dirty the card. I put one in the card table for the card in which a pointer was changed. So for each, when a pointer is changed, I mark the card, and then I'm sure that intergenerational pointers can only be on cards that are called dirty, that have a 1-bit set in the card table. Yeah. Right. So sometimes there will be like an object that goes from one card to the next. You always, usually when this happens, you decide to mark the beginning of the object. But you can decide, you can say, I only care about the specific field, if the field is in the... This is like an engineering decision, and both of them will work if you can later find the pointer that was modified and trace the young generation adequately. Yeah. No, this is the only thing we have. Yes. Yeah. So this is another decision that has to be made, and so whether I check if there is an intergenerational pointer and then I mark it in the card table, or I do it for any pointer modifications. I mark it, and usually what will happen is that I do it for any pointer modification, and the reason is that I usually, if you look at time. So there is like times of garbage collection, and then there is execution of the program. And most of the time there's an execution of the program, and so the write barrier happens all the time, and you want to keep it as small as possible. Right. So the garbage collection suffers from that, but it operates in a smaller scale. Like most of the time, the program is running and you want to make the write barrier as short as possible, and the garbage collection will suffer from it. And we'll talk about it soon. So for now, assume that any pointer modification is going to dirty the card on which it resides. Okay. So, but we are sure that whenever there is an intergenerational pointer, it must be on a card like this. Couldn't be on a card that's not dirty, that has a 0 bit in the card table. So the collector, when it comes, it scans all the dirty cards and, of course, the roots, and from them it finds all the intergenerational pointers that have to be on dirty cards. So the collector it goes through this card, all the cards that are dirty, and looks for intergenerational pointers in the old generation, and it also goes to the roots, and after that it can trace the young generation and see what's reachable. Yeah. It just what is the question is, why is it better to just mark when a card is changed and not check that it's really pointing to young generation? It's just that it's less costly. You remove the check, right? Right, you will pay for it later. But for example, imagine there is a card. Let's think what happens. There is a card and there are a few pointers that change on it. And say 2 of them are intergenerational and 5 of them are not. So this card is going to get dirty anyway, whether you're going to check it and whether you're not going to check it. But if you don't check it, you run the program a lot faster. And then during garbage collection, in any case, you have to go through the entire card and find intergenerational pointers. So in cases like this, and usually with locality of program, there are few modifications on each dirty card. So what happens is that it will not matter a lot. Sometimes it will matter, but then we make the consideration that we want the program to run as fast as possible and maybe let the collector work more later. Generally, you don't need these cards, but if you're going to, mark any modification, then you don't want even to check if it's in old or in young. You just mark the card table. And I will say, I don't know if it says here, Okay, so the collector goes through the dirty cards, and if there's a dirty card that doesn't have an intergenerational pointers because pointers were moved or we just marked it carelessly, then it's going to just clear the bit, and then it will not need to go over this card again later in subsequent collections. So this is it. And in terms of what's bad and good, so this is bad for the collector indeed, because it must scan the whole card, maybe to find just a single intergenerational pointer, and it's 1K bytes that it has to scan in order to find this pointer. And it has to be done again and again. If there's a single intergenerational pointer in a card, then anytime I do this young generational collection, I have to go through all the dirty cards, and for each of them, I have to go through all the pointers and see if one of them is intergenerational. So if there's just one, I'm wasting a lot of time. So this is really not good for the collector, but for the program, this is really good. So there were all kinds of papers suggesting that you can do it with a specific hardware in 2 instructions of machine code and stuff like that. You could do it really fast. Even if you don't do that, you take the address of where you're changing the pointer, you shift it to get the number of the card, and then you just go to the right place and set the bit that correspond to the card that was changed. This can be done very fast. So it's a lot faster than adding something to a set, whatever data structure you use for that set. So this is good for the program, bad for the collector. Um, this thing, um, okay, and there's a question, can we improve? So this is a really bad thing that I go again and again and scan the same card to find the pointer that I need, the intergenerational pointer. Does someone has an idea of how I can, use both remembered sets and card marking in order to make it cheaper for the collector and still efficient for the program? I want it to be. I want to win from both worlds. Okay.
Maybe you can make each pointer multiple sides. Then you can, instead of search of the whole generation, you can just go to where the pointer points back.
That will be costly to do that. But think of it that I have to go over the card and find that pointer, and I have to do it again and again in each young generation collection. What could I do to, yeah? Cool. Exactly. This is what was suggested. So what you want to do, you don't want to repeatedly scan for each young generation collection where the intergenerational pointers are. So when you scan a card, you can say, I found an intergenerational collector. The collector, I'm going to add it to a remembered set that I maintain. So, and then I will not have to scan the card again in the subsequent collections of young generation. So I do a sweep of a card and I find the intergenerational pointers, I add them to a remembered set that I maintain, and then the card is not dirty anymore. So if the program will change it again, I will scan it again. But if it doesn't, I don't need to scan this card again. So this is called remembered sets can play cards. Nice name for this method by two young researchers. I'm going to talk about them, young at the time, not anymore. So the program just does the light right barrier. The best thing for the program is to just mark cards when a pointer is changed. That remains the same. So the program still uses this really light right barrier, but the collector, it doesn't scan the cards repeatedly with each young generational collection. It it scans dirty cards, it updates the remembered sets with all the intergenerational pointers that it finds, and then it clears the dirty bit of the card, and it doesn't have to scan it again if it's not changed again. So the remembered sets are then used for a very fast collection because for the collector, it goes through the remembered sets to find all the intergenerational pointers, and it doesn't need to scan cards after that. So it's a fast write barrier, and the collector scans a card at most once per modification of the card. Yeah. If a pointer is modified by the program, then the card is. Yeah, so I scan a card and I have the intergenerational pointers in a set. If the set, I have the locations of intergenerational pointers. Maybe it's changed and it's not anymore intergenerational pointers. I'll remove them from the remembered sets if they're not anymore, pointing to intergenerational pointers. If the program then goes again and changes the card, maybe a new intergenerational pointer is installed there, then the program has to dirty the card again, and the collector will have to scan the card again. If the program changes the pointer to not be an intergenerational pointer, what will happen is that the collector will go to its remembered set and see this pointer from the previous collection. It will see that it doesn't point now to something that's an intergenerational pointer, and it will take it out of the remembered set. It will have to scan the card again to see if there is no new intergenerational pointers there. And this is how it will work. So it will always be correct. There will be settings where this will be less efficient or more efficient, but usually it's very good. Cool. So this is the remembered sets can play card. Tony Hosking was like a PhD student. He was a doctoral student at Amherst, and Hudson was also a young generation, a young researcher there. So Hudson did like a master's studies, and then after that he just remained as a research associate in University of Amherst, and he did a lot of work without becoming a professor, without doing a PhD, like a doctoral studies. And so this is Tony Hosking. He was the PhD student. They were both guided by Elliot Moss, who is one of the authors of the book. I will talk about him. We'll get to him later. And this is Tony Hosking in Beijing in 2012. He was born and raised in New Zealand and Australia. When he was, he did his undergraduate, like his BA in New Zealand, and then he came to the US to do a PhD, and there he did all this work with Elliot Moss. He did a lot of work on garbage collection, also on transactional memories, which I don't know if you've seen. It's something with parallelism. And Tony also visited us. This is in the Sea of the Galilee, in the Kinneret, and then here he is in Haifa. So this was the third method. And the fourth method is maybe the simplest. I don't know if it's better, but it's used once in a while. So what you do, if you change a pointer, what you do is you just add its address to a buffer. So you have a buffer. Whenever you change a pointer, you add it to the buffer. And later, during collections, the collector goes through this sequential store buffer and adds them, if needed, to the remembered set. So this means the program just writes pointers to a buffer, and the collector does what it wants with them. This is the way it works. The properties are a small overhead for the program, but buffers get larger and larger as the program runs. You can decide to stop and do a garbage collection in order to not let the buffers go very large. It's similar to remembered sets, but work is deferred to the collector. The program does not have to do addition and deletions from the remembered set. So that's the fourth way to do it. Questions about recording intergenerational? Yeah. Mhm. So you're saying you're talking about sequential store buffer or in general? In general. So you're saying there will be a lot of pointers from young to old, and if we recorded them, we do not. That would be a really huge remembered sets, sequential store buffer, and stuff like that. We don't do that because there are lots of those. What we do is we collect the old generation together with the young. It's a small addition, but then we don't need to know if we don't need to record intergenerational pointers in the backwards direction. So we just scan the young generation and we see if anything is reachable from the young generation. We just scan them together. And so we do full heap collections and young generational collections. We never do old generation collection. Okay. So the second thing we said we need to handle is when do we promote objects from the young to the old generation? And the thing that has to be said is that we don't want to use clock time. We don't want to say this object has been living for a minute, therefore it's old and needs to move up to the upper generation. Uh, because it depends on the machine, it depends on what the program does, and so forth. We don't want to do that. What we do is we can count bytes of allocation that could serve as the time measure for the memory management system. That is perfectly fine. Usually, I just count the number of collection, which is a rough way to count allocations, because after enough allocations, there is a garbage collection. So with a low resolution, I can ask how many garbage collections did the object survive after it was allocated. So this is the way we want to do it. And we have some trade-offs. If we take a small young generation, then we'll have short pauses because we just have smaller area to reclaim when we do the young generation collection. But we'll have more collections because there will not be enough space to allocate before we need to reclaim again. So this is and of course if it's larger, then we have longer pauses but fewer collections. This is clear. So there is like a trade-off. Yeah. The clock time. So suppose I'm saying, after a minute for me, you go from young to old, and then you buy a new machine that works 100 times faster. I'm exaggerating, yes, but and then in a minute you finish the program and you never cycles of the CPU. That's better. But maybe I go through a period where I don't allocate anything. I multiply matrices and I don't do any allocations for that. Then, once in a while, I will promote everything to the old generation just because a lot of time has passed and I didn't do anything that's related to allocations or reclamation. So it doesn't fit this concept very well. So if you count the bytes of allocation or with low resolution, you count the number of garbage collections that have gone through an object, then it's better to decide that it should be promoted. Okay, so trade-off one is the size of the young generation. Trade-off two is how fast to promote. So there is a promotion threshold, and this is normally I would use a space for each age, so I will be able to know what's the age of an object. And promoting, so I could promote fast, and then I will have more space in the young generation because everything goes out. And but the problem is that if I promote fast, then dead objects may be promoted. So they are promoted and then they die. They're still young. I promoted them fast. then the young, and then I have these old generations with lots of dead objects, and I'm not going to reclaim that for a while, and then it's a waste, like dead objects in the old generation. I expect very few of these generation objects to die. Okay, so trade-offs are clear. There's nothing, again, mathematical to say about it. You have to decide your thresholds by your experience or according to your system's behavior, the environment that you're in. Um, there is a way to do adaptive tenuring, which allows you to not decide ahead of time, but just work with it. So you, what happens is if I get to an object and I need to either move it to another semi-space of the young generation or to promote it to the older generation, then I don't get a full view of what's going to happen in this collection. I'm going one object after the other, and I have to decide where to put them, to leave them in the same generation or to promote them to the next generation. So I don't have an overall view of how many were promoted and how many remained. And so sometimes we want to do adaptive tenuring to decide how many to promote, but we just don't know what's happening in the general view. So we look at what happened in the collection when it's done, and we say, if you promoted too much, then we want to promote less in the next generation, so let's put the bar higher from promotion, and then fewer objects will be promoted. And so I can just raise or lower the bar depending on what happened in this collection, and it will affect the next collection. And hopefully, the program behavior is steady, and therefore this adaptive tenuring will work, and eventually I will get to a stage where I have the right parameters tuned. So this is the way to go if you do not want to determine ahead of time what will be all these parameters. There has been some work on multiple generations. Like I said, someone did 7 generations. The good thing is that in the intermediate generations, you can let object die before they, dirty the old generation with dead objects that you do not reclaim. But the problem is that you need to manage all these generation, all these intergenerational pointers, and also it's more code, it's more complex. You need to do all this, and usually people do not want to do that. It's simplicity is also a factor in deciding what to do, and many times we just do 2 generations, young and old. Okay, so to summarize generations, most collections are short because the young generation is small, and there's good locality both for the program and the garbage collector because they all look at the smaller space and use it mostly, and there is approved efficiency because the young generation has a lot of dead objects that I can reclaim. And this is in spite of all the overhead that I get from recording intergenerational pointers and all of that. So it is widely used. I think almost all collections in productions are like that. The one problem that's remaining is that when you do the full heap collection, it's still a long pause, and you will suffer from it. And the question is, how do we do full generation collections without long pauses? And this is the topic of the train algorithm. Hudson is one of the guys who did the remembered sets can play card. This is the guy I did not talk about. And Elliot Moss is the advisor, the professor that guided them. And so the train algorithm says, I want to collect the old generation incrementally. So I'm going to work on it, part by part, and I'm not going to do like a full collection of the entire heap. And therefore, it will be also short pauses when I collect the old generation. There will not be a large pause. So whenever I do a young generation collection, I do part of the old generation collection, and and this was employed a while ago by a Java virtual machine. It didn't survive. No, I don't think anyone does it today, but I think the idea is nice and it's kind of educational to understand this algorithm. So we'll go through it. This is the train algorithm. Elliot Moss is the was the advisor. Uh, he had so he spent his career mostly on memory management, and he did a lot of interesting algorithms. This is one of them that we'll see. And he had lots of graduate students, lots of students who finished their PhD and did a lot of good work. And he was in Amherst. The University of Massachusetts at Amherst is a bit west of Boston, maybe 2 hours drive, if I remember correctly. And he's an author of the book, if one of the three authors of the book. So that's Elliot Moss. If you want to see the full picture, this guy who is eating all the time, terrible. He retired recently, maybe 2 years ago. And okay, so we can talk about Rick Hudson after the break. 20, yeah, in 30, 11:30. Rick Hudson was start after his masters. He stayed as a research associate in Amherst for a while, and he did many papers on the memory management. And also about parallelism. He then went to work in Intel for a while, for maybe 10 years. And then he spent 5 more years in Google, and then he retired. He did in Intel, he did a lot of work on parallelism, and in Google, he worked on the Go programming languages and did garbage collection for that. And he's now retired. Cool. Okay, so the train algorithm is what we came here for. So the structure of the heap is that we have a young generation, as we usually have in this generational collection, and the old generation, which in the days of the politically correct times in the US, they called it mature object space. And we don't put in these two objects that are very large. We put them in a separate space, which is many times done. You don't want to move large objects in the young generation between the semi-spaces. And we'll see that for the train algorithm, also in the mature generation, you have to move stuff all the time. And so we don't want to do it with large objects. There are very few large objects usually in the program. You can just put them, do mark sweep over them. Actually, they didn't even do mark sweep. What they did is they had representing record. They had like a small object that was allocated in the young generation and then was promoted to the older generation. And that was when this was reclaimed, they knew that the old object could be reclaimed. So there was just a representative who was copied and not the large object, which is a nice idea. Okay, so in the old generation, what we want to do is to collect it without long pauses. We want to be able to reclaim dead objects. And the first try is just let's, divide the heap into some, let's divide the heap into some, let's call it, they called it cars. This is the heap. I have here space. The entire heap is divided into, let's call it cars, like kronot in Hebrew. It's we have we'll have a train soon, but now we have cars. And for each of them, let's keep a remembered set of which, pointers are pointing inside a car for each one. And also, of course, for the young generation, there will also be a remembered set. So whenever you change a pointer, you put it in the adequate remembered set, or you do card marking and then the collector will put it in the right remembered set. So, and now you do a young generation collection, and then you do one of those. And then you do the next young generation, you do another one, and so forth. And therefore, you will reclaim everything eventually. And there is one problem with that that is good to notice. So, I mean, the way we will do this is we will look at what's reachable from the remembered sets and from the young generation and from the roots, of course, as usual. We have the roots. And then we will reclaim what is not reachable from remembered sets, young generation or roots. Problem? Why can't I do this? Yeah.
Couldn't you make one in a different car be a new object that has a reference to something in the car we're currently collecting? So that's the
So if this
and it would have been promoted.
so if this happens, then I will see this in the remembered set. And then I will not reclaim the target of
Future, then
it will be updated in the remembered set. Any other problem? So the problem is, and it's always hard to see it in the beginning, is if we have a cycle, the same problem that we had for reference counting. So what happens is if we have here's someone that points to this and here's someone that points back, then we don't have, and each time we only work on a single car, then there's no way to reclaim these two. And, when we say cycle, we mean strongly connected component. Any strongly connected component that is split between two different or more cars, we will not be able to reclaim it. And so and the same problem we had with reference counting and we have here, you should beware of cycles when we do things locally, because cycles we don't want to trace the entire thing. Each time we're working, we want to do just a single one. If we do each time just a single one, we don't have the global understanding that this is a strongly connected component, and so we cannot reclaim any of these. So this is a problem. So the way to work with it is to partition the old generation into cars, but group cars into trains. So I take cars and put them in trains, and now it will work. What we want to, so for each train, we have a remembered set for the train, which is just the remembered sets for all the cars minus those that point inside the train for one car to another. Okay, so it's all the pointers that come from outside the train into the train. So this is a remembered set of the train, and our goal will be to move such cyclic structures, so these strongly connected components, into a single train, maybe between different cars, but eventually all of the strongly connected component will be in a single train, and then we'll see that there's nothing coming into the train, only this cycle, and we will be able to reclaim the entire train. Yeah. We will have to take care of that. This will be the goal. We will want this cyclic structure to be inside the train, and everything else will move out. And then the entire train will be reclaimable. There will be nothing that points into this train from outside. Right. So if I had a global view, I never have a global view. If I had a global view, I would just, move this cycle into some train, and know that I will be able to reclaim it. But I will have to work without the global view and somehow get into a situation where this cyclic thing gets into a single train and everything else is out. Then I will be able to reclaim it, and this will take some effort to get to that without looking at a global view. Only each time I will look at a single car, and this will somehow happen. Oh, yeah.
Why does everything else need to be out of the frame for us to be able to?
The way I will work is that I will just free the car. So, in general, so first I will say, whatever way I work, I want if to identify that there is a strongly connected component. I need there to be nothing pointing into the train, which I can check quickly. I don't have to go through all the cars. I can only look at a single car, but I can look at the remembered set. So each time I collect a car, I will first look whether the entire train, there's nothing pointing into it, and I will know that I can reclaim the entire train. If I have something that's pointed from the outside that's not part of the strongly connected component, then I will not know that the train is reclaimable. It will not be reclaimable. There will be some objects who will still be reachable from the outside, and then I will not be able to reclaim an entire train. Okay? But the way I'm going to work with it, I'm going to go one car at a time and then move everything that's reachable from the outside and then free the entire space after I move any reachable thing from it. And if I collect a full train, if I have a train, then I will just free this entire space. If there's nothing pointing into the train, I can free the entire space of all the cars in the train. Okay, so the goal is to move cyclic garbage structure into a single train and collect the full train. Leave it there alone and collect it. And the avenue is I'm just collecting a car. I don't have a global view. What is this SCC that I'm trying to put in a train? So when I'm collecting a single car, I have to move all the reachable objects out of this car wisely so that I will be able to make the cyclic structure get into a single train. And okay, so this is how it looks. And I'm going to start by reclaiming the first car in the first train. And after I move all the objects that are reachable outside the car, I can reclaim this. So these are the numbers are logical. This doesn't have to be near each other in the heap, right? There are cars which are really subsequent. There are consecutive areas in the heap. This is really consecutive, but this doesn't have to come after it. It's logically belonging to the same train, but it's not right near each other in the real heap. So I have this train with 4 cars. I'm doing the first train and the first car, moving all things that are alive out, and then reclaiming this. And then I'm going to this, moving all the things that are reachable out, and then I reclaim the entire space and so forth. So this is the way that I go. And from the point of view of the remembered sets, I only need to record pointers from a larger car to a smaller car. Why is that? Because when I get to this car, 6 will not exist anymore. Because I'm going according to this order, if there is a pointer from 6 to 9, when I do the collection of 6, it will move out to some higher car, and then I will have to do the remembered set of, to update the remembered sets of 9 adequately to show this pointer. But if there is a pointer from a lower car, I don't need to know it because I'm going to reclaim this car before I reclaim this car. Makes sense? So I only, yeah. Yeah, I only have intergenerational, not intergenerational, inter-car pointers recorded from a higher car to a lower car. So for this car, from its point of view, everything that comes into it is recorded in its remembered set. But if there is a pointer from car 1 to car 2, it's not recorded in the remembered set of car2, just because when I will do the reclamation for car2, car1 will not be around. So I don't need to keep it because things will move out. If there's anything reachable here, it will move to some other car and then it will be in a larger car than 2. And then I will put it into a remembered set. There's no way I will reclaim car 2 and I will need to know about something that's in car 1. And in general, if I have a pointer from 2 to 7, I don't record it because there will be no car 2 when I come to collect car 7. Okay?
Does that mean you all cards in all screens the access?
I do each time I do a young generation, I do 1 car. And then when I do the next young generation, I do 2.
מניח שכאילו, כי דברים תגיע עכשיו לקו 12, ויכול להיות שכן יהיה לו כמה פוינטרים בקו אחד.
Yes, I'll have to have a write barrier. The collector will also have to update the remembered set. If there will be a pointer from here to 1 or to 2, then it will have to be in its remembered set. So suppose there is a pointer from here to here, and when I collect this, I move it, I don't know, to here. When I move it, I have to put it in the remembered set because now it's in a higher car. But as long as it's in a lower car, it will not be there when I go to collect car 2. Yeah, okay. So I only have to keep half of the pointers in the remembered sets, those that go from high to low. Okay, so when I want to collect a car, I mark objects that so first of all, I do a young generational collection whenever I do a car collection. So I know all the pointers that point from the young generation, of course from the roots because I go over the roots. I know everything that points to my car from young generation and roots. And then if I see that nothing pointed to my car or my train, and the remembered set is empty, either for the car or the train, then I reclaim the car or the train. So the first thing I do is check if there's nothing pointing inside the car or nothing pointer inside the train, and then I can completely reclaim the entire train or the entire car. This is the easiest case. There's nothing that is reachable inside the car or the train. Okay? Otherwise, okay, so now this is not the case. The simple case is gone, and now we have pointers pointing to objects in the car. Okay, and we have to work. So if there is an object that's referenced by the roots or the young generation, then I move it to the last train. Okay, if the last train is full, I make a new train and put it there. Okay, and what does it mean to be full? This is kind of threshold, this is kind of heuristics that I decide. But generally, if I have something from the roots or from the young generation, I move it to the last train, or if it's too large for me, I put a new train for it. Okay, this is the first thing I do. Second thing I do is no objects are reachable now from the roots or from the young generation, only from other cars. Because whatever is reachable from the roots or the young generation has moved to the last train. Okay, so now I look at an object and it's referenced from train K. Then I move it to train K to the last car, or I open a new car. Why do I do that? No? Think of my goal. What am I trying to do? Yeah?
Yeah, we want to collect cycles, so we want to get everything that.
Exactly. We want, if it's pointed by something, probably that something is in the same cycle. If there's like an unreachable cycle, they will point to one another and we want them together in the same train. So if something is pointed by train K, I want it in train K. So I move it there. Yeah.
Is there any rule to choose if it's reachable from multiple trains?
Excellent. This is a question that I usually ask next, but since you asked it, maybe, so the question is, what happens if I have like a train k plus 3 and train k, I have pointers to my object in my current car that I'm collecting. Where is it better to move it? You also have an answer. Okay.
I think we can move it into k plus 3 because when we reach train k, we will just move both to k plus
Right, exactly. So it's better from, I could move it to k, but then what would happen is when I go to reclaim k, I will move it to k plus 3. So let's just move it immediately to k, to train k plus 3, right? Instead of moving it to k and then when I reach it, moving it to k plus 3, let's move it immediately to k plus 3. So this is if I'm if it's pointed from multiple trains. Okay, so now there's everything that's pointed from the roots is gone. Everything that's pointed from the young generation is gone. It's not in my car. Everything that's pointed from another train is gone. It's not in the car. So the only thing that's left is are objects that are pointed from the same lower train, but from higher cars. So suppose I have an object that's referenced from another car in the same train, then I just move it to the end. Okay, if I need, I open a new car. I maybe it's part of a cycle that's inside the lower train. I don't want to move it out. I want to keep it so that I will eventually move everything else out, and this one will be reclaimed with the entire train. So it's better for me if I keep stuff that's not pointed from outside in the lower train. Okay, so whenever an object moves to a new car, all its descendants in the collected car are moved with it. So, for example, if I have, I am moving, I have, this is the lowest car, and this is pointing to another object. I could wait. I could say, let's move this up, and then update the remembered set, and then discover that this is referenced by something else, and then move this to the same train as I moved the first one. But instead of doing all that, I'm saying, if I move this, then I take with it everything that's reachable in the same car. I don't go out and back in. I cannot look outside my car because that will take more time. I'm limited to one car, but anything that's directly reachable in that car from the object that I'm moving, I will move with it because just to save time, it will move in any case. Okay, so this is saying this, and for each moved object, I install a forwarding pointer. I need to know, so if I move an object, maybe there will be other references to it which I'll have to fix. So I need to know where it moves. And also maybe another object here will point to it and I will discover it later. I need to fix pointers. And so I keep a forwarding pointer in every object that I copy, and I update pointers to O by the remembered sets will tell me everything that points to any object in this car, and I'm going to fix all these pointers and move objects if needed. So that's it. Okay, that's the algorithm. I just go one car by one car at a time, and I move object wisely like this to other cars, to other trains, and things will go well with this. So we need to see this. So when all objects have been copied out, the current car can be recycled. And the interesting things are, if the current train has a cyclic garbage cluster, so there is some strongly connected component that is not reachable from outside the train, any object in this cluster will never leave the train. Because if it's not reachable from outside the train, then it will never leave this train. On the other hand, if there are live objects that are reachable from somewhere else, these will move out of the train. So we are sure that anything that's reachable will move out of the train, and this cyclic structure that is not reachable from outside the train will stay in the train. So what will happen eventually is that we'll just have this cyclic structure entirely in the train, and we just can reclaim the entire train. Okay? Yeah.
And it will be usually in the last car, right, of the train?
Yeah, we move everything, but it will spread over many cars. If it gets into a single car, it will be easier. But it could be spreading over 10 cars, and we'll take everything out, and it will be in the first and last 10. It will be the only thing in the train. Maybe there will be two clusters that will stay because both of them are unreachable and they cannot leave the train. And then we just reclaim the entire train. Yeah. So how many times I need to do car collections in order to get everything out and be left with the cyclic object? That was, I think, maybe that will be a home exercise. I think we used to give it. So I'm not sure if we're giving it this year or not. So, but it's an exercise. No, it will take more than a single pass over a train. You could put things in an order that will be difficult. So, for example, if you take a pointer from the second to the first, and then from the third to the second, and things will start rolling, and then you could create structures that will make it last longer. But it will be finished. You can show there is a limit. I only do one car in a garbage collection. I never move more than one car. I mean, I could choose to do 3 cars, but it has to be fixed, not dependent on pointers or something. I do one car. I take big enough car, and then I do one car per young generation collection. Okay, so this is the idea. Here is an example done by some student in the old days. So what you see here is we have 2 trains. And in this train, you have this cyclic structure that I want to identify and reclaim somehow. And there is this line that is reachable from the root. And there is this object that is reachable from outside the train, but it's also a cyclic, unreachable structure. So what happens? So if I look at these, where should R go? According to the recipe we gave, R is reachable from the roots. And so, yeah, it should go up to the last train. And if it's too large, we can make a new train. But here, it should go to the last train. A is reachable from train 2. Where should it go? To train 2, yeah, join his brother. C is not reachable from outside, it's reachable from another car, so it should go to the end of this train. And there is space. In this drawing, there's space for 3 objects in each car, just for the drawing, for simplicity. Okay, so here is how it goes. Excellent. So the route went to the last train. A joined his brother, and C went to the last car. The cycle is still in the lower train. Yeah. Only in the same car, I take the descendant and move them together. Yes. Yeah. Yes, root always goes to the last. Root and young generation pointers are always moved to the last train. Yeah. Okay. Oops. Well, so what do we expect now? So, so we are in this car. S has a pointer from the second train. Where should it go? Second train. D is pointed from the same train. Where should it go? Same train, and is his descendant should go with it. So S goes up, and these stay in the same train. And now in the next young generation collection, I collect this car together with the young generation. And now T should go up, and we're in this great situation where the cycle is all in the first train. And now we can reclaim the entire train because there's no pointer from outside the train into this train. So great. So now we're in this situation. And now I want to go to train 2 and reclaim the first car. So the drawing is going to put train 3 here. It's higher, but it's going to be lower in the drawing just to keep train 2 here. Okay. So let me first ask you what you expect. So R is pointed from the roots. Where should it go? Last train. Suppose we open a new train, train 3. Uh, A and B are not pointed from the outside. So we'll just not touch them. They will disappear. And we're not going to move them because they're not pointed from the outside. So here is R, and this can be reclaimed, the entire space. And last thing is I want to reclaim this car. So S is pointed from the third train. Where should it go? Third train. And this is pointed from S, so it will go with it. And they will both. And now we're done with this example. But it should be clear that we're just looking at a single car and moving things out wisely, and then the global view becomes nicer. It becomes that all these SCCs that are unreachable remain in the lower train and then are reclaimed together with the full train. Yeah.
Can you repeat where we can, where exactly do we know that we can reclaim the entirety of train?
Entire train is just because there are no pointers into that train.
Those we have remembered.
Yeah, remembered sets we can look at. We don't look at other cars, but we do look at the remembered set of the train. Okay. Properties. So we have all generation collected incrementally. We have the algorithm reclustering live objects. And this is good for locality because when I touch an object, many times I touch its descendant later. And if they're close together, then it's good for locality. So this is good. And periodically, we copy all reachable live objects and we reclaim everything that's not reachable. This happens in time, not immediately, like if we did an all generation collection or full heap collection. Okay, so there is a bug in this algorithm. And the bug is not that it will be incorrect, but it will not make progress. There is a way, very improbable way. It will not happen in real life. And even if you wanted to write a program that will create this progress bug, it will be very difficult for you. And this was found by Seligman and Grarop a bit later. So let's see how it works. This was like Seligman was the master student, and he found this. Grarop was his advisor. And Seligman later went to work in Hotspot, where they created the most advanced JVM at the time. He found this problem and suggested a way to fix it, and that was his master's work. Let's see what's going on. What can go wrong here? So here you see two objects, and say just for the simplicity that you cannot put them together in the same car. Maybe they take more than half of the space of the car. Otherwise, you can create more objects. You can put more objects here and it will be the same. But so you have these two objects, they are alive. So there's a route pointing to one of them, and they're never going to leave the first train. So let's see how we engineer that. So I come to collect car 1, and I see that the object is pointed by another car of the same train. So I will move it to a third car, right? This is what the algorithm dictates. I'm afraid that these are unreachable and I want to just keep A in the train. And so now A will be in car 3 and B will be in car 2. And what we expect is that when I reclaim this car, B will go to the last train. And then I'm done. I made progress. But after I reclaim this car, the program starts to work and it can change pointers. So the program could move the route to point to A, and I go back to exactly the situation where I started. So I have this object, and the route points to his brother who is like in another car. So, and this could repeat. So I could go over this again and again, and each time I move one object to the last car, the program comes and moves the route to point to the object in the last car. So here is the next thing. I moved B, and then the program moved the route to point to B. And each time I work, I never get these live objects out of the first train. There's nothing there. There are lots of other trains with objects to be reclaimed, but here there's just these two objects that are alive and just never leave this train, so I cannot go to the next trains to do real good work. So this is a bug, okay? Everybody understands this is a progress bug. How would you solve it?
You can change the order of the trains. Just go with it once in a while.
It's a worst case situation. So, the adversary can just, you change the order arbitrarily, and the adversary always knows how to always point to the car that you're not reclaiming at this point. This is like, this will never happen in real life because the program has to know that you've done this young generation collection and moved this, and this
This
is.
one's the bug because this disrupts reclaiming lots of trains.
Yes, you cannot go on reclaiming. You have just this train with these two objects, lots of other trains with dead objects, but you never get to that.
Why am moving the train that want to be reclaimed to a different location and then reclaims out some trains? Why doesn't it solve it? I mean,
What you want to? I reclaim one car at a time. So what is the solution?
you reclaim one car from one train.
Yes.
And because that is here, so we don't move on to other trains, right?
No, I reclaim. I move this. If I go back, from my point of view, I moved A to another car, and then I reclaimed this car. Right? I moved here, but when I got to car 2, I moved another object. Maybe there are 50 objects, and I moved them to another car each time, and just you know,
Maybe I still don't understand why this is considered a bug.
in a global view, I'm handling these live objects and I just move them inside the same train. I never reclaim any dead object.
Because you don't move to the other trains.
Yeah, this is how this algorithm works.
The solution is to force moving to other trains.
Yeah, you want to stop, so like name this train to be last. When do you do this? But you have to decide. But how do you? Maybe these are not alive, right? This could be a garbage cycle that you're living there, and you'll never. I mean, yeah, but I want a solution that works. Yeah, yeah.
Move things pointed to other routes every time.
This will be great if I could say I'm collecting this car. There's nothing here, but there's in another car. There is a route. Let's move it out. But I'm not like it's not fair to touch other cars because I don't have the time to work on another car. Yeah.
Expansion.
Not there is like if I need to put an object in a train, I will open as many cars as I wish, because I want to. If there's a large cyclic structure, I want it to fit into a train. There's no limit on the number of cars in a train. There is limit if I'm just putting arbitrarily in the last train. I will say maybe I want 5 cars in the last trains. If I don't need to put an object there, I will open a new train. Okay. So what did Seligman and Grarop do? They did really, it's not very nice, but they did a brute force thing. They said, whenever I do a collection of a car and I move nothing out of the train, I call it a futile collection. Okay, collection, a car, it's a futile collection. And so, and when I do a futile collection, so in this case, I'm moving A to the last car, and I'm moving nothing out of this train. For me, this is a futile collection. I'm not making any progress. What I'm going to do, I'm going to remember one of the pointers that come out from another train into this train. Here there's just one, so I remember this, but there could be many. I will remember one of them. And when I get to collecting that car, I'm going to think of this pointer as still existing. Okay, so if I came to this situation, for me, I remember with this car that there was an important, I don't know how you want to call it, but there's like a sticky pointer that I want to remember that pointed to B. B is going to go out of this train. And if it was a route, then it will move to the last car. So it's a very focused solution. It's not very sophisticated. It's just say you had the futile collection. Remember one of the pointers from outside the train into the train, and that pointer sticks. Even if the program moves it, for us it still exists when we come to reclaim that car. Okay. So it's just special monitoring. If no object moves out, the collection is denoted futile. And when encountering a futile collection, I record an external reference to the train. There has to be one, otherwise I can reclaim the entire train. And it is not in the first car, otherwise it will not be futile. So I just remember, I record this reference, and it's like a route for when I get to this car and I reclaim it. Cool. Okay. Questions? Okay. So they also suggested to look at popular objects. These are objects that, if there is like an object that is referenced from many other objects, then when I'm going to move it, I will have to fix all these pointers, and it's going to be disruptive and take a lot of time. And then they just say, let's have cars with popular objects, and we don't collect them. Probably these objects are alive. There's so many pointers pointing to them. I'm just going to take this car logically and move it to the last train. And so non-popular objects are evacuated as usual, but the popular objects are just taken with the car and it's moved to the end. Okay, that was their thing. To summarize, the train algorithm, it's incremental, it's short pauses. I have the young generation plus one single car. It does partial compaction and clustering. So when I move stuff to a new car, I of course do it in a dense manner from the beginning of the car. So there is compaction done, and it's copying, but there is not much space that I need to reserve. I don't keep double space for copying. It's like partial copying. The disadvantages is there is some time overhead for repeated copying, so I move stuff between cars all the times. And there is space overhead because I need to keep all these remembered sets and to manage all the cars. I have to tell myself, this car belongs to this train, it's this number in the train, and so forth. There's management to be done. So takeaway, is we can work locally each time on a single car and get some global benefits. Eventually, we got all these strongly connected components into the lower train and we could reclaim it. And this is really nice. And this is something you could think of if you have problems like that. You want to work locally, but obtain some global understanding about what's happening, then there are ways to do it. And also beware of cycles or strongly connected components. You need to worry about them if you work in small increments. And so this is the train, and generally for generations, it reduces most of the pause times and all of the pause times if you do the train algorithm together with the generational collection. And it improves efficiency by concentrating on where garbage exists, and it improves locality of collector and the program, and it's widely used. So
Widely used or not widely?
it is widely used. Yes.
Not train algorithms.
Train algorithm, no. We don't see it in production today. It was used in production a while ago, but it's a nice algorithm that I think we should know. But the train algorithm is not widely used. This is about generational collection in general. Any more questions? Okay. Okay, so see you next week.